We'll start. All right, I'd like to present to you Henryk Krawczynski from Washington University, the greatest physics department in the world, right, Henryk? And he's going to tell us about X-ray polarization, both from balloon experiments and satellite experiments. Henryk, I will give you a 5-minute.
Okay, I hope you hear me. So I'm talking about X-ray polarimetry, and want to acknowledge briefly collaborators on the right-hand side, graduate students, and Javier Garcia, Katya Sokolova-Lapa, Matthew Liska, and the IXPE and XL-Calibur teams. So I want to briefly introduce the experiments and then focus on modeling I've been doing for black hole observations and show you a new fitting model, kerrc, and show you first results when using that to fit intermediate state Cygnus X1 data, and then for the best fit show you the predicted IXPE results. Let's see, so IXPE is a NASA-led mission with a significant Italian contribution. Martin Weisskopf is the PI, works from 2 to 8 keV, 600, 700 square centimeter effective area, 13 arc minutes diameter field of view, angle resolution 30 arc seconds, and energy resolution about 20% for its half maximum. It's working with a photoelectron polarimeter. So a photon comes in, ejects a photoelectron in the direction of the electric field vector, and then you get like after the gas electron multiplier, get a picture of the electron drift path and get the direction of the electric field vector. That's a polarimeter. That was the experiment at BAL. And maybe most importantly, here's an approximate sensitivity, 99% detection level, confidence level detection is the minimum detected polarization is 1% for 100 milliquark source that's being observed for 120 kiloseconds. So you get really 2 very low polarization fractions for strong galactic sources and first detection of extragalactic sources. And then here's like the preliminary first year observation plan. Interesting, the black holes. Cygnus X1 GS 1915, and then the TOOs include like additional 3 black holes in outburst, looking at the soft and hard states. So overall 40 sources will be detected. This shows like, oh, that was all I had for IXPE. The show XL-Calibur, the predecessor experiment for the upcoming XL-Calibur. So that measures at higher energies, 15 to 80 keV. It's a balloon-borne experiment, 51 scientists, 19 institutions. It's a mirror polarimeter, it's a scattering polarimeter, photon scatter perpendicular to electric field vector, and pointing system points like with half an arc second accuracy at sources. The new experiment, maybe you heard about the old experiment, which we flew in 2018, detected the neutron star GX301-2, got some constraints on polarization. That's the QU plane where 100% polarization is the outer ring. So we constrained the polarization. The new experiment will be much better because it has the Japanese Hitomi hard X-ray telescope spare mirror and improved shielding, more compact polarimeter. That's a longer focal length, 12 meter focal length, and then there's some prediction of sensitivity, like so for half a crab you get like below 1% within 100 kiloseconds. That's a predicted neutron star sensitivity. You can see you can like look at models and distinguish between different models with pretty high accuracy here. The observation, so there are 2 planned flights, one for 5 to 7 days in 2022 from Sweden in May, and one in 2023 for 50 days, 40 to 50 days from McMurdo around the Antarctic. For the first flight, want to look at Cygnus X1 and together with NuStar IXPE, and Crab Nebula and Pulsar, and flaring sources. Briefly show you here a simulated multi-wavelengths campaign. So we applied and got data on NuStar and NISA. This shows kind of anticipated results. You see here NuStar, NISA and NuStar, the two focal length, focal plane modules. Then for IXPE, then you see here it has the Stokes I, Q and U information, and you see here clear detections, even though in this particular model it's only 0.5% polarized. At higher energies, get the XL-Calibur data, where you see also detections at this model, let's say like polarized, like 3 to 5% here in this range. So it will be exciting to get this multi-wavelengths data. Motivation, of course, is to constrain the inner structure of the accretion flows. Look at the disk structure for different states, accretion regimes, get the corona location and shape, measure black hole spin and inclination, get at accretion disk dynamics, study oblique accretors, bodies in Peterson alignment, warps, or accretion disk waves, and hopefully get information about the origin of QPOs. Test general relativity seems ambitious given the astrophysical uncertainties. Been a number of review articles about that. And then don't cover jets in this talk. Want to identify clearly the energy carrier, Poynting flux, electron positons or protons, the magnetic field structure, the emission model, and get information about jets, how jets form. Okay. Briefly, just you've seen the beautiful image of the polarization of the radio emission from the Event Horizon telescope. In that case, it's mostly synchrotron emission, which is highly polarized, also kind of remarkable, or should be noted that there's a strong Faraday rotation and conversion. For X-rays, kind of interesting, contrasting that with the M87 observation that the stellar mass block, how black holes evolve much faster. So if we can look at different accretion regimes, we see the thermal emission from the accretion disk. So we really witness the conversion of gravitational energy into radiation. We get some spatial information because harder thermal X-rays come from the inner portion of the disk. The softer come from the outer portion. And Faraday rotation conversion, QED by refringent are most likely negligible. That's for all kind of photosphere and magnetic fields smaller than 10 to 8 Gauss approximately. And the main process that generates polarization is then scattering of the disk and scattering in the corona. Just briefly mention Lee et al. In 2009, Schnittmann and Krawczynski studied the polarization of the thermal emission and found that you can determine the inclination. Can also kind of get an independent measurement of the spin because there's a transition between the kind of horizontal polarization far away from the black hole to a more perpendicular polarization close to the black hole where many photons orbit the black hole, and the returning emission causes a polarization swing that manifests itself in a minimum of the polarization fraction as function of energy. So you can kind of, by measuring the minimum, you can estimate the spin. Briefly here, go through things that have been studied for polarization. So in the corona, photons scatter, get polarized. It's described by the Fano scattering matrix that includes a Klein-Yeschiner cross-section. Jeremy Schnittmann had a nice paper where he compared sandwich corona to spherical corona with a few additional follow-up papers. For example, we studied the impact of Klein-Yeschiner cross-section, the contribution of synchrotron emission, which is pretty negligible. Zhang et al. Had additional modeling, and for example, their code has been used to study the effect of absorption in the disk for the resulting polarization. Net effect is that absorption is pretty negligible for higher spin systems where the matter is higher ionized close to the black hole, and more significant for lower spin systems. For reflection, just mention Mikhail Dovchak studied the polarization in a simple lamppost model, assuming the coronal emission is unpolarized. Javier Garcia, who's in the audience, is now doing a detailed radiation transport to get the polarization of the reflected emission. So that's in progress. I want to show you. So I've been working on two models. One is like an extensive library of simulated configuration for fitting high signal-to-noise multi-emission data. And the second approach is a collaboration with Liska et al. To weight trace two-temperature general relativistic radiation magnetohydrodynamic simulations to reveal qualitative features. First mention one and then go to two. So this developed a new fitting model. It's called kerrc. Self-consistently simulates a comptonization in 3D coronas. That gives absolute fluxes and energy spectra of the thermal comptonized and reflected emission, consistent with the accretion disk and corona geometry. Includes state-of-the-art reflection modeling. So I use a silver reflection spectra from Javier. The metallicity, electron temperature, electron density, and spatial variation of electron density are fit parameters. Overall, this includes a data bank of 63 million energy spectra, reflected energy spectra, and this uses a self-consistently derived ionization parameter and photon index as function of the radial distance and accretion disk. It also accounts for the inclination dependence of the reflected spectrum. The code also simulates the comptonization before and after the reflection. So even if you reflect a line, it still gets comptonized if it hits a corona. The simulations also cover the polarization, and in principle, you can also derive transfer functions for temporal studies. Briefly mention how the polarization is done. The disk emission is done with the Chandrasekhar results for a definitely deep electron scattering atmosphere. The polarization 4 vector is parallel transporters. Compton scatterings change the polarizations. And then the disk scattering uses Chandrasekhar result for the polarization that depend on the incident angle of a ray, of the reflected angle of the ray, and the IQ and U of the incident angle. This is combined with Excel model to get a model like the amplitude of the reflection, but the polarization properties are taken from this Chandrasekhar formalism, which should actually be pretty good, given that it depends on the geometry of the beams. So it simulated a library of 45,360 configurations, and this includes like a family of configuration which go from different wedges of different extents and physical parameters all the way to kind of spherical configurations, and then a second family of conical coronas which kind of sit in the funnel region above and below the black hole. This is kind of the model, and you see it's a large number of model parameters. For the results I show you, a lot of model parameters are kept constant. For example, the metallicity of the reflecting gas, or assume a constant electron density in the photosphere. Don't play with the inner cutoff and outer cutoffs of the emission. Briefly validated the model against kerrc, and you see here for different inclinations that the results agree very well, and also validated the Compton engine in terms of the spectrum and the polarization with a Monk code developed by Wanda Zhang and Michael Dobchak. So the agreement's really nice. Just want to show you first results from using this to fit the data, and John Tomczyk and collaborators kindly shared the data with me. These are plots from their analysis, where you see like Suzaku data. I think the data themselves were taken in 2015. The paper is published 2018. And you see if you just fit with the power law, you see the clear iron K alpha emission, Compton hump, if you have a complex model, you can kind of account for most feature with some deviation still. So the chi-square per degrees of freedom was significantly different from 1. So thanks for sharing the data. It's really helpful. Don't have to, it's quite non-trivial because the Zaku data are kind of saturating. So the Zaku has 5 kiloseconds. I only use XIS3 data, and the NuStar data has 20 kiloseconds. So to show you the preliminary results, this is a fit of the best fit wedge of sphere model. It actually turns out the best fit in this family is pretty much a sphere, because the wedge has an opening angle of something like 65 degrees. You see that the IONK alpha line, I also kind of included, like Tomczyk et al., a reflection of interstellar matter, which is non-polarized. You see that overall the model doesn't fit very well the IONK alpha line. It kind of takes a strong reflection of interstellar medium or surrounding clouds. And but overall, you see kind of it describes qualitatively the spectrum. The fit of the conical corona is slightly better. So the chi-square is 3,174 instead of 3,724. And you see also the IONK alpha region is kind of described better. Still, like a chi-square, kind of similar contributions from all areas of the spectrum. For example, here, low energies, there seems to be something different in the data. I'm not sure that systematics of the data or a real feature. So to show you a bit the internals of this bed-fitting conical corona, because now you can go into the accretion disk and see what's raining down in terms of photons hitting the corona. So this is the best fit. An age kind of close to the official value. The best fit spin is very high as previous results. The corona and this conical corona is very close to the black hole. 2.5 Rg is the lower limit, extends to 20 Rg. Maybe what's else interesting? Densities and logarithm of the density is 19, so it's 10 to 19 per cubic centimeter. And to show you, this is, for example, as a function of radius, the intensity of the thermally emitted radiation, and then the returning emission is really intense, and it actually dominates the energy that hits the accretion disk up to 10 Rg or 5 or 6 Rg, at which point you kind of get then the coronal emission starting to dominate. But it's really important that in the inner region, you have a very strong returning emission. At the inner edge, you get like a lot of brightness just from the little bit outer radii, and emission kind of hits the inner emission after going around the black hole. This shows the ionization parameter of this the best fit model. So it's very highly ionized at the inside and then kind of drops. This is the photon index. It's very hard inside and then kind of gets a bit softer. This is a 1 to 10 keV photon index of the emission hitting the disk. This is kind of interesting. This is kind of as a function of distance from the black hole. You see here, these are the energy spectra of the Chandrasekhar reflection, but this is then as a function of inclination of the emitted, of the reflected emission. And this is the Chandrasekhar preliminary reflection, which is then reweighted with the Silver models. And for this higher ionization degree, you see that the Silver model has featureless. And then as you go outwards, let's see if I can get this, you get further away from the model, you see that the ionization degree drops, and you start seeing the line features in the Silver model. So the ratio of these different models is basically uses to reweight the simulations and then to get the reflected energy spectrum. This is then still Comptonized, and then you get the real reflected energy spectrum. So as you move further away, you see kind of the intensity on the left-hand side here, the intensity drops. You see this, the scale kind of drops, and you get more prominent line features. This shows like the overall for like the closest simulated node to the final fitting result, the overall thermal and Comptonized emission, and the reflected emission, including the Comptonization. You see with the resolution that I use for fitting the data, you see here the kind of the broadened IOK alpha feature. So this is kind of what I wanted to show you, fitting the data. I'm kind of excited about it because you kind of, so the best fit model is a conical corona, very close to a black hole. Let me show you the results for the predicted polarization for IXPE. So this is the best fit wedge sphere corona. You get, like, as a function of energy, the I, Q, and U, and you see polarization fraction is pretty high, 6.5% at 4 kV. That's kind of partially because the reflected emission is pretty highly polarized. This shows
5
the best
minutes,
fit.
Henrik.
This shows the best fit conical corona. You see that they're significantly different. So the polarization is lower and goes to a minimum close to 2 kV. Okay. This is kind of the theoretical model that goes into the Sherpa program. This is like simulated IXPE data, where you see that Stokes I, Q, and U are measured with very high precision for 300 kilosecond observation. So it kind of should be possible to measure these differences between these two models, and the polarization should be easily detectable with IXPE. Just to mention these I energy spectra, the flux has always a much better statistics than the polarization data. So if you want to get independent information, you have to just fit Q over I and U over I. And without going into detail, let me just kind of summarize that just on the polarization data alone, we think we can measure the spin with an accuracy of 0.05. The inclination with 10 degrees, and the orientation of the inner accretion disk in the sky with plus minus 30 degrees. I want to finally briefly touch on the GRR-MHD simulation, and Matthew Liska already gave you a beautiful talk on Monday, I believe. This is collaboration with Liska and Tchaikovsky, Kowshik, Razi, Oliver, and Gibra. You probably saw beautiful results with a lot of accretion disk physics being revealed in these simulations with unprecedented spatial resolution. The two temperature promise to give us a vertical energy transport in the disk, and maybe or hopefully give some prediction of the corona properties. I want to show you some first results. So this, the Matthew Liska's results were then weight traced by my graduate student Andrew West. He modified our code to work in kerrc coordinates. And I want to show you this beautiful movie that he did on the, hopefully that works. Let's see if I can click here in some ways. So on the left-hand side, you just see the density of the misaligned accretion black hole, and you see kind of the disk kind of starting to stabilize and then doing some quasi-periodic oscillations. On the right-hand side, you see the weight trace results. The color shows the intensity, and the bar show the polarization fraction and direction, like the length of the bar is the polarization direction, and kind of if you focus really in, you see kind of how this evolves in time. So these results are still being in production, and we are generating light curves and polarization light curves, and the aim is to look if we find QPOs in I, Q, and U, and what we can learn about quasi-periodic oscillation based on these results. And then we're also looking at energy spectra average over different timescales. Just wanted to mention, you probably may have seen beautiful paper by our competition, Kinch et al. They a beautiful simulation. It's not yet self-consistent with radiation simulation. So they kind of have a cooling function which gives the shape of the accretion disk, but they have a beautiful radiation post-processor which gives you simulated lines. What's kind of amazing that it looks like the width of the line may not depend on the spin, but more on the accretion rate. So there's a few surprises coming with this. So these are Beautiful results. Just to summarize, so IXPE and XL-Calibur will be launched soon. IXPE, December 13th. That's a likely date, I think. Other missions I didn't mention: Integral measures polarization, AstroSat, Polar Light. LEAP is a proposed all-sky monitor that can measure the polarization of burst, and EXTP is a China-led mission that's similar to in sensitivity to IXPE. The polarimeters plus existing X-ray satellites will test models developed over the last 60 years. I showed you this new fitting model, kerrc, and the first results are fitting Suzaku and NuStar data. There's a few insights. Conical corona seems to fit the data better than wedge or spherical coronas. Returning radiation is super important, and higher fidelity fits require dedicated silver calculations where you account for the contribution of the thermal emission to the plasma ionization. It's just a lot of radiation coming from below that also impacts ionization, and the non-power law energy spectra hitting the disk. So it would be really interesting to use the result from this simulation and put them into silver and get more customized silver results for this. The reflected emission leads to a rather high polarization fraction that are easily detectable by IXPE, and these predictions will be tested soon. Didn't have time. I also have quite a lot of results of magnetars where you can distinguish between different surface and atmosphere models and detect strong QED effects. Okay, thanks.
Okay, thank you, Henrik. Please post questions in the Slack channel. And I don't see any yet. Do we have any questions from the floor?
I see John.
Oh, John. Okay, John, go for it.
Okay, thanks. Nice talk, Henrik. Let's see. So the question I wanted to ask was about the POGO plus upper limit on SIGX1 in the hard X-rays. You showed that on one of your plots, and then you showed, the much better sensitivity that that Excalibur will get. However, in their paper, they have some pretty strong conclusions about the source geometry based on that upper limit, saying that the corona must be very extended. I'm just wondering if your predictions, differ from their predictions.
So if I remember correctly, I think they had an upper limit of 8%, which is consistent with my model predictions. Not fully sure why the model prediction is different. Kind of the simulations are much more detailed, and this one is based on an actual fit of the Suzaku and NuStar data, while their model was just kind of hypothesizing that most of the emission is reflected emission. In this case, actually, as you maybe saw, that the reflected emission is still kind of not fully dominant over the other emission. But I think it would be interesting, and it's really important to have these polarization observation together with broadband spectral observations, so you can really fit both and get them. So don't have to postulate that reflection is the only emission component, for example.
Can I make one more comment, or actually two more comments? I want to email with you about the SIGX1 results. I've got some thoughts about the residuals that you're seeing. So
that's very cool.
So we can connect by email afterwards. And then finally, COSY is also a polarimeter, so it could have been on your first.
Oh, it should be. Okay.
Thanks. That's it.
Okay. Anything from the floor?
Yeah.
Before?
Yes, there are two questions actually.
Go for it.
Hi, here is Agata Różańska. I have technical question really, because silver works for constant density, and I guess you want to rely this assumption or not.
Right. So right now I didn't rely it, but I did in some of the fits, but not in the ones I used here. So the silver is the code on it calculates all the geodesics, stores like how many billions of geodesics, and convolves them with silver when you fit. And it's a very fast C++ code that does that. So you can use the full silver for each little radial bin on the accretion disk. So you can use
Yes.
non-constant density.
But you know, my question is because if you rely this assumption, you are meeting thermal instabilities in your calculations.
Right.
But
so the thermal
actually,
instabilities.
you do not meet. You have no chance to meet it, right? In the such
Right.
an organization of your code, because
Right.
other computations are showing the existence of thermal instability, and many times they are limited on it.
Right. Yeah. So
Maybe
this
we
is
can
kind
discuss
of,
it.
yeah. But the
later.
idea, I think actually that's a good point you bring up. I would like to make this code a public open source with everybody having ideas of how to modify profiles to implement them and see what it does, you know. I think that's, but the idea is you couldn't put this in and see what it does, but the code is flexible enough that you could modify and whatever you think is the density profile, including thermal instabilities, you can test here, you know. And it's good to derive that from first principles, but I think it's good to have a flexible parametric model like here, where you can try to fit the actual data. I think if you only have first principle simulations like this one's from Kinch et al., you will just get something that's very different from the data, and you don't know what to do to reconcile data with observations. So I think there's a role for this parametric, but it hopefully will evolve in time as 2T temperature GRMHD simulations improve. But I think there has to be a dialogue between first principle and fitting so that we get at the physics.
Thank you.
Gulo, if you can be very quick.
Okay, very short question. Hi, Henrik. Thank you for the great work. Do you have like strong constraints on the dimensions and the geometric properties of the conic corona in Cygnus 6.1?
So in this model, the opening angle is 21 degrees, the best fit opening angle. I'm still simulating the error bars on these, but they're pretty small. In the model, it only has kind of a sliding corona. That's right now it's at the fit converged at the lowest possible value of the corona, which starts at 2.5 Rg and goes to 20 Rg. And then in the model, this family of coronas, the corona slides out, for example, from 10 to 50 Rg or from 50 to 100. So right now, I'm kind of the model that was the best fit goes from 2.5 to 20 Rg. And it's pretty optically thick. It has like 1.9 optical depth and an opening angle, which is pretty large, 20 degrees.
Okay, thank you.
I think we have to end it here, but there's more questions for you, Henrik, that will be popping up on Slack. So take a look at the Session 8 Slack channel. I think Sarah's got some questions for you. And let's thank Henrik again.